I don't know, like we sold a lot of it. It's like over 500.
Okay, here's your last homework. It's also posted. You want to start it? Okay, what we're looking at here is equilibria in reacting systems. That's what we started discussing last time. And our equilibrium criterion can be stated this way. It's a summation here of the stoichiometric coefficients times their respective chemical potentials. That sum equals to 0. And each of these chemical potentials we can write out as equal to its value in the standard state plus RT times the logarithm of the activity. And that activity is defined as the fugacity divided by the fugacity in the standard state. So what we can imagine here is plugging in for each of these and then see how this comes out. So when we do that, we end up with this quantity n plus and this sums to 0. So what we've got here is actually refers to the standard reaction, so we might refer to that as delta G0 reaction. So that's the molar Gibbs free energy change of the standard reaction. What we mean by the standard reaction is when all of the participants, reactants, and products are in their respective standard states. So it's hypothetical reaction. So let's look at the second term here. One thing we can notice is I can stick all of these coefficients here in as exponents. And then I may recall that if I have the sum of the logs of terms here, that's equal to the log of the product. Remember that, just for math. So I should be able to write this term as equal to a continued product here. So what I end up with here is the log of the continued product of all of these activities, each raised to the stoichiometric coefficient power. It's just a different way of writing out the math. So I end up with this whole term RT times this. Now this particular thing that I've defined here, is everyone okay here with continued product?
Could you explain that?
Yeah, sure. So the continued product here of xi would be equal to x1 times x2, times x3, and so forth for all of them, over all I. Okay. Now I define, I didn't mean to write it that far in. This thing is defined as K, and we call it the equilibrium constant. So this is a bit of a mess on the screen here, but you all understand me?
Not the natural log part. Not the natural log part. Just the
argument of it.
Okay, you didn't accidentally erase that. I just want to make sure. Okay, thanks. That sounds right.
So let's write this whole thing as we've got it now. What I've got is delta G here for the standard reaction plus RT log K equal to 0. So if I rearrange this thing, then I can write out it explicitly for the equilibrium constant, which is what it is we're going to be interested in, especially here, which is, as I've just defined it here, this continuing product of the activities raised to their stoichiometric coefficient powers. That's just definition, and I see what that is now is equal to the exponential of minus the standard Gibbs free energy change for the reaction over RT. So that's just this equation now put in a form that we can actually use to solve problems. Now just to illustrate it here, we have the composition and pressure involved over in this term that involves the equilibrium constant. And over here we have, just for the standard reaction, a quantity that's going to allow us to evaluate K at the desired temperature. Just to illustrate this for the reaction that I've been using just to illustrate things. Let's just write out what K is here. So that would be the affinity here for species C cubed, I'm sorry, the activity, times the activity for species D over the activity for species A times the activity for species B squared. So I have to go to the next page now. Let's assume it was a gas phase reaction. And that means that I can write down for each of the activities the mole fraction times the fugacity coefficient times the pressure. So if I write out then for K, where the gas phase reaction of A plus 2B goes to 3C plus D, it looks like this. A little bit of writing to do here. Oops, already I make a mistake. And I could split this out, it may be evident just looking at it here, into K formulated in terms of Y, times a K phi, and times pressure. Here I've got, you can look at these exponents, that's going to be an exponent which is the sum of the stoichiometric coefficients, which is the thing that I have identified here as a stoichiometric number for the reaction. Works out to be, for this reaction, just +1. So you can see that if I have value for the equilibrium constant that I can obtain somehow at the desired temperature, then I should be able to go backwards here and solve for the composition of the equilibrium system. Okay, so let's look at what I call the usual problem. And that is to be given of course, you have to be told what reaction it is. So the reaction statement, and then we have to be given the initial state. So let's call it the initial inventory, which is a collection of initial mole numbers for everything that may be present, including inerts. And this is usually a matter of taking a basis. And then we have to, of course, be given the physical variables, temperature and pressure. So given that, the usual problem is to be given that information and then to be asked to determine the equilibrium composition. For a gas phase reaction, for example, then it would be the equilibrium set of mole fractions, the YIs, corresponding to equilibrium. So we solve these problems basically in 2 steps. And the first step would be to obtain the value of our standard Gibbs free energy change of reaction, and hence the equilibrium constant. So we get a numerical value for that. This is hence K. As soon as we have that, we have K. At the temperature of interest. And once we've got a numerical value for K, then we can use it, as I've indicated up here, to solve for composition. And the way that's done is to solve for a single variable that describes the entire composition of the system, and that is the equilibrium value of my extent of reaction xi. And once I have that, I can go back and solve for all of the composition that might be of interest. I have, as I've indicated up here, K is equal to this. So let's proceed with looking at these things. First of all, at this issue of getting the value for the equilibrium constant at the desired temperature. We get K from that. For the whatever reaction it is we're interested in. Well, we should pause and think about this for a moment. You could imagine that we might have tabulated values for the standard free energy change of reaction for a whole range of reactions, but that would be essentially an infinite list. So it's unlikely that we would find that directly. But what are tabulated are standard free energy changes of reaction for formation reactions for thousands of compounds at a reference temperature of 25 C or 298.2 K. So what we find tabulated here, as I said, are formation reactions. At a reference temperature equal to 25 C, which is 298.2 K. So we can find these listed for many compounds. Let's first be careful to understand exactly what we mean by a formation reaction. So the definition is a reaction, and this is for a given compound. So it's a reaction forming 1 mole of whatever compound we're interested in here from its elements. In their standard states. At 25 C. So that's the definition here of what we mean by a formation reaction. And these are tabulated for many reactions. Let's just say here for an example, for formaldehyde, that compound is CH2O, and we note that it is a gas in its standard state. So the formation reaction would be form it from its elements, each in their standard state. So carbon, and it's common to remind ourselves of what the phase state would be for that material in its standard state, plus hydrogen, which is in its gas state, plus 1/2, of course, oxygen exists as a diatomic molecule, so we have to write it that way. The gas state equals 1 CH2O, and that's in the gas state. So there's the formation reaction with everything designated as we normally do it. And we should hope to be able to find tabulated the value for this at 25 degrees C. So somewhere in here I've got that. And it's the first one in my list. Formaldehyde, and you'll notice that here, if I can blow it up a bit, I've got the standard for energy of formation here at the reference temperature, given in values here, kilojoules per mole. So there it is, minus 109.99. You notice in this same list that I've got values for the standard enthalpy, or heat of formation, in the same units. And this is just the beginning of a much larger table that you have in your appendix of the textbook. So what we've got evaluated here is this thing for energy, standard for energy change of formation, 298 for this compound. Now it should be evident that for any reaction that we might have of interest, that we should be able to formulate the standard for energy change of the reaction out of the respective formation reactions for all of the participants in the reaction. So for any reaction, I can form the standard for energy change for it. Is just equal to the summation of the stoichiometric coefficients here times the respective formation reactions for the different compounds. So is that sort of clear? So we can do an example of this. Let's say that our interest was oxidation of ethylene to formaldehyde. And that reaction would be, reminding myself of the phase states. So for this reaction, that's also gas. So for this reaction, I have 2 times lots of stuff to write here. Minus the standard for energy change of formation for the ethylene, minus but what about this guy? The formation of an element from an element, of course, is just 0, so that's trivially 0. So I should be able to go and look up these numbers now. So for the formaldehyde, I've already obtained it. That's minus 109.99. And for the ethylene, I'll have to go look at, here it is. So that's minus 68.15. So the standard heat of formation works out to be minus 288.13 kilojoules per mole. So out of this now I should be able to get the value of K. Let's go over to the next page and do that. And I remind myself, this is K now evaluated at 298. And that's the exponential minus standard energy change of reaction over RT. And I have to remember now this is in kilojoules, so I'm going to use a value for R, which is formulated in terms of joules. So I better multiply by 1,000 here to convert that over into joules. Then I can use my 8.314 joules per mole degree K. And this was at 298. When you write 298, that's an abbreviation for 298.2 or 0.15, whatever you use. And this works out to be, here I got a minus and a minus, so that's an exponential of a rather enormous number, which is essentially infinity, that reaction, as we say, goes to completion, because the equilibrium constant for it is so enormous. But I used that as an example since I had the data so handy in that table. But if we're interested in another temperature than 25 degrees C. That means we have to look into the issue of the temperature dependence. Of the standard reaction, and of course, along with it, K. So we have to go back now to look at the more fundamental issue of the temperature dependence of a Gibbs free energy quantity. And so let's go back to our fundamental equation for that. dG is equal to minus SDT plus VdP. And we're looking at the case of constant pressure. That's all at the standard pressure of 1 bar. So it's just minus SDT. But what we note is that we can write S here out as, well, just remembering that G is equal to H minus TS. So S can be written here as just G minus H. Sorry. And that can go in up here. And what that gives us is, let's just write it, it just takes a couple lines to do it. Or I can put it in the standard form of first order ordinary differential equation, and that gives me so the way we solve those, and we can always solve them, is the first order ordinary differential equation with a functional coefficient. And we can put it into the form of a total derivative using an integrating factor. So, presuming you remember that from your math. And that turns this, when I multiply it by the integrating factor, that turns it into so I'll just remind ourselves. And this enormously important equation, anybody know the name of it? Is the Gibbs-Helmholtz equation. And it'll give us the free energy dependence on temperature, and we see that it's tied up intimately here with the heat of whatever it is we're talking about. For our particular interested in, the G quantity that we're interested in is the standard heat of reaction. So I can just rewrite the equation as it would apply there, and that would give me D of standard heat of reaction over T with respect to T is equal to minus, now the corresponding enthalpic quantity is the standard heat of reaction over T squared. Now I can, this is just a rewrite of the Gibbs-Helmholtz equation applied to the situation that I'm interested in. But I may recall the standard heat of, or standard Gibbs free energy of reaction is minus RT log K. So the quantity I want over here, delta G, standard of reaction over T, is just equal to minus R log K. So I can substitute that guy in over here, ending up with minus R d log K dt equal to minus delta H standard of reaction over T squared. Hope I got enough room, yeah. So I can get rid of the minus signs and write this as d log K dt is equal to the heat of reaction, standard heat of reaction in this case, over RT squared. So here's another form of the Gibbs-Helmholtz equation which relates it directly to the equilibrium constant for the reaction. Anybody know the name of this equation? This is the Van't Hoff equation. Actually, one of the Van't Hoff equations. So it's going to be our way of getting an equilibrium constant at the temperature we're interested in by integrating away from the reference temperature that we have data plotted for or tabulated for at 25C. So we can take a look at that, see where that brings us. Let's go to the next page for it. And a bunch of writing here. So I'm going to have log of K at some temperature of interest here, T, will be equal to its value here at, I'm going to abbreviate that as at 298, and that's what we got by putting together the formation reaction values of the standard Gibbs free energy change at the reference temperature, which is the 298.2. Then plus the integral from that reference temperature to whatever temperature it is we're interested in of d log K dt with respect to T. But what we've shown is that this is equal to the standard heat of reaction over RT squared. So what I've got is the general relationship for the equilibrium constant here at any temperature of interest is equal to, and now I can plug in the value that I just on the previous page worked out for this. It's convenient to write that out. Would be minus delta G reaction, and I'm going to get rid of that subscript because we really don't need that. Oops, that's too much. So this would be minus the value of the formation, I'm sorry, of the standard Gibbs free energy change reaction at 298 over R times 298. So that's what this is. Plus, and then I have the integral here from 298 to the temperature of interest of standard heat of reaction for RT squared dt. So at this point I haven't made any approximations, and so I've might box this as our general result for getting the equilibrium constant at any temperature of interest. And so now we can see what it takes to be able to deal with this. And it's evident that we're going to have to deal with this guy. So the heat of reaction is what it says, and this is the standard heat of reaction. And I've written it here without any reference temperature, so that would be itself a function of temperature. So, this is and we have to remember what that's going to be. But before we do that, let's make an approximation at this point, assuming that that's going to be effectively constant with temperature over the range of interest. And that would mean that presumably we wouldn't be too far away from our reference temperature of 25 C. We'll look at that in more detail as we get into this.
I saw that coming. Why, if we can make that approximation about the enthalpy of reaction, why can't we make that about the Gibbs free energy of reaction?
Right here, you saw what the temperature dependence is from the Gibbs-Helmholtz equation. So if this, by saying that it's constant, it isn't saying that it's zero. What you're implying is that it should be zero, so that the...
I'm just, you said that within a small temperature range you can model the enthalpy of reaction as being constant, right? I'm just wondering why
I'm showing you right here why we can't.
Mm-hmm. Okay, how?
To make that assumption, it's equivalent to saying the heat of reaction is zero. And I'm not saying that, it's almost never zero. There is such a thing as an athermal reaction, but it is really rare. The enthalpies associated with these chemical reactions are usually quite large. But there are many situations, particularly for small molecule reactions, where it's pretty nearly constant. So let's take a look at the situation where we'll say that it is constant. So it is, and I can pull that through the integral sign, and this gets much simpler. No, I need to write it like that. Now pulling that through, and I'll pull the R through at the same time. That's equivalent to taking